3, 2, 1. Okay, so welcome to our next colloquium in the CLSP Spring Seminar Series. Just to announce, next week's colloquium speaker will be Jordan Cohen from Dragon Systems, and his title will be, I'll have to get the alignment, A Problem in Speech Recognition Research with Examples from Astronomy. So that will be next week.
Right up your alley, Paul.
Okay, so today it's our great pleasure to have speaking to us Mark Johnson from Brown University, Department of Linguistic and Cognitive Sciences.
Around the other way, but that's
cognitive. Well, we know who's
right.
First.
That's right. Yeah.
It's a great pleasure to have Mark. Mark is really an ideal person to be speaking to this group, especially given the audience. Mark did his PhD at Stanford University, where he worked on both the formalism and the linguistics underlying some of the so-called feature-based approaches to grammar, and did some very interesting work on looking at what kind of formal power is required to analyze certain for example, among other things, certain analyses of Dutch syntax and what kinds of things he said about the underlying formalism. Since then, he's done a variety of things, ranging from more linguistics, looking at just computational properties of different kinds of grammar formalisms, some computational investigations of psycholinguistic models, and a whole range of other things. Today, he's going to be talking to us about some work that is sort of a more recent thread in topics that are dear to many people around here, in particular work on some kind of language modeling and probabilistic grammars. So today he'll be talking about context sensitivity and stochastic unification-based grammars. Thank you very much.
Yeah, so actually I was looking, when I was invited to come down here, I looked around for a title that would try to be, or actually not a title, a topic that would be broad enough to encompass the interests of all of the various different groups that would be here. And so I hope I've got something which is interesting to at least some of you. Of course, I run the danger that, in fact, actually I'll be able to offend absolutely all of you in this process. So I'll see how that goes. So the structure of this talk there are really sort of 5 pieces. One is, why am I interested in doing this work at all? Why am I interested in trying to combine linguistics and statistics? Then I guess the next 3 parts are really sort of very detailed technical work, talking about, how exactly I propose to do this. So I'll be talking about the problems that context sensitivity poses for the problems of learning stochastic models, and then actually come up with a couple of suggestions of approaches for solving those problems. And then actually at the very end, since this is the home of optimality theory, and since a number of you here are working on OT theory, I thought I'd actually try to see if I could tie together the maximum entropy or log linear model approach, which I'll be suggesting in the previous 3 sections, compare that with OT theory, and I think I want to show that there are several very close connections. Well, why does it make sense to even start to think about combining linguistics and statistics? So, roughly speaking, I think what linguistic theory is really concerned with is describing possible linguistic structures or possible interpretations for utterances. Whereas I think those of us that are interested in actually modeling processing, either human processing or building a machine which can mimic human processing in terms of understanding or using language, in general, we're actually not just interested in finding the set of all possible linguistic analyses or interpretations. We also want to find the most plausible interpretation as well. So I sometimes sort of like to say that linguistic theory is a possibilistic theory, whereas a theory of processing really needs to be a probabilistic theory. That is, you want to have the most probable or most plausible interpretation. I think one could actually have a whole talk, justifying why one wants to work probabilistically. based on evidence from human psycholinguistics. But one thing I thought I'd just sort of throw out there is to say that if you do start to do any psycholinguistics, the very first thing that you need to control for is frequency, right? I mean, if you don't, all these other effects which we know and like to study, you know, about the effect of syntactic structure and stuff like that, those are all second order effect compared to the effect that frequency has. And so, you know, I think that actually shows that, yeah, frequency matters a lot. Why do statistics? I mean, those of you that used to work on, like me, used to work on unification-based grammars, there used to be a big argument about what the difference was between these so-called declarative theories and the more procedural theories. I think actually statistics and actually OT theory, which I think is related to that, is declarative in that same sense. I could go into more details on all these things, but in fact, I think what I'm going to do is spend just a few minutes going over this last point here. I think I want to show that approaches which rank interpretations or rank analyses actually solve what I'm going to call the two biggest problems in non-statistical computational linguistics. And that, I guess, this is really the motivation for why I'm interested in statistical approaches. So what are these two biggest problems in computational linguistics, non-statistical computational linguistics? One is that ambiguity explodes combinatorially. As the sentence gets longer, the number of possible analyses usually doesn't double with sentence length, it explodes multiplicatively. So I'll actually be I'll be using a little corpus in the later part of this talk, and I've just pulled out a couple of sentences from it. This is a corpus of basically derived from repair manuals for photocopiers and home center multifunction devices. It was put together by the Xerox Corporation. So these numbers up here are the numbers of analyses that a linguistically detailed grammar that the people at Xerox PARC have been writing since the year dot. You know, this grammar has just about every linguistic constraint that they can think of putting in there. And nevertheless, they're still finding, you know, hundreds of analyses for quite normal sorts of sentences. One thing I'd like to actually point out is that, you know, the linguists in here might think, well, presumably there are some more linguistic constraints that you could actually throw in here. Let me just simply say that I've been down that path, and I can tell you in practice actually what happens is that usually refining the grammar is self-defeating. You can add some more constraints which reduce the number of analyses of one sentence, but it usually increases the number of analyses of other sentences. So roughly speaking, what happens is that as you refine the grammar, what used to just simply be, say, a single noun phrase, now is going to be a noun phrase that's marked to be a count noun phrase versus a mass noun phrase. That may help you disambiguate some examples, but there's going to be other examples now where you've actually introduced an ambiguity. Noun phrases that where you can't resolve whether it's a mass or a count noun phrase. And so in fact, actually now you have two separate analyses. One where you're interpreting the thing as a mass noun phrase and one as a count noun phrase. So in fact, actually refining the grammar actually makes things worse. In fact, I sometimes think that it's the job of the linguist to actually point out that sentences that seem to be perfectly innocuous are actually many, many ways ambiguous. And it's the job of the computational linguist to try and figure out a way of working out which of these is more likely to be the right interpretation. So,
can I just
stop
you just for a second? You
sure.
just actually provided the justification for one of Fred's claims, long-standing claims, that every time he hires another linguist, his hit rate goes down.
That's right. Yes, that's right. Exactly, yeah. Yeah. So it should be kind of obvious that preference information is the type of thing which can actually help a parser navigate its way through this huge forest of possible interpretations, right? One thing that I think is not so obvious is that the same preference information actually helps us solve what I would call the second major problem of non-statistical computational linguistics. And that is that you get no analyses of many perfectly comprehensible sentences. So in particular, requiring linguistic well-formedness tends to lead to non-robustness. So notice that the standard approach to the problem number 1 is to make the grammar more refined, rule out possible interpretations. The standard response to problem number 2, in order to be able to find analyses of sentences like he walk, for example, somewhere where there's a failure of number agreement, is actually to make the grammar looser or sloppier. But notice what happens is that if you decide to ignore agreement, permit there to be a well-formed sentence where the subject and the tensed verb phrase don't agree in number, is that you can no longer use number as a feature to disambiguate a sentence like the following one. I saw the father of the children that speak or speaks French. Depending on whether or not speak or speaks is singular or plural, that's actually going to determine whether or not it's the father or the children that are the French speakers. And in fact, actually, what happens is that in non-statistical computational linguistics, people spend a lot of time talking about extra-linguistic repair mechanisms or mechanisms for just simply collecting phrases that are left over after you've completed your parse and build it into some sort of tree. One point I'd like to make is that, well, that's all very well and good if the goal is to produce a tree. But if the goal is to actually not just produce a tree, but produce some kind of semantic interpretation, there's no guarantee that the tree that you've produced by just collecting leftover phrases can receive any kind of interpretation at all. The point I want to make here, however, is that once we start to think about analyses as being ranked, we actually receive a systematic treatment of robustness as well as preferences. So, suppose we actually define a probability distribution over, and you'll see I'll use a little, that's not a W, that's an omega up there, meant to represent a linguistic configuration. You can think of that as a pairing between sound and meaning. The point is that generation and recognition involve two different conditional probability distributions. So when you're generating, what you're really looking for is, out of the set of all possible pairs that pair this semantic input with different phonological outputs, you're looking for the optimal pair. So if we imagine optimality is going this way, we're going to select this pair and produce this particular phonological output. On the other hand, if what we're doing is recognition here, what we'll see is that, what we're given is the phonological input. And we're solving a different conditional we're trying to maximize a different conditional probability distribution, namely one that involves these two analyses here. So this is actually an example of where the same language model can produce an interpretation for a phonological input that it would not generate given that same semantics. Right? Not only that, if you think about this little phonological representation over here, it would never be generated. This phonological representation is like the form he talk. There's always a more optimal phonological output for every possible semantic input. But nevertheless, if this is if he talk is the input that you're given, there is in fact actually a pairing that associates it with a semantics. So in fact, you could obtain a semantic interpretation for it. So the point is that inside of a, inside of a model with that has some kind of preference or ranking information, we get explanations not only for how it is that we can prefer how it is that we can find a preferred interpretation, but we also get an explanation for how it is that a single system might actually be robust and might be able to interpret things that it would never possibly generate. Well, that's all very well and good, but what exactly might these probability distributions look like, or what might these rankings look like? I think there are several different stories that are worthwhile investigating here. I think optimality theory is a very interesting approach, but the approach that I'm going to take here is one that's more statistically oriented. Right, so the idea is that, in fact, that syntactic theory, well, actually, so far this in fact actually is so general that in fact it actually includes optimality theory as an instance of it. So a syntactic theory, theory of linguistics, defines a set of universally possible linguistic structures. For what I'll be talking about today, I don't care about whether they're universally possible or language particular. Then I have a family of probability distributions on this set of possible structures, which is parameterized by a parameter vector. And this is actually sort of all fairly standard. In fact, those of you that know something about Chomsky's principles and parameters approach, this shouldn't really worry you too much at this standard. Nor should learning, what I've said here about learning, worry you too much. I mean, basically what I'm saying is that learning involves actually finding the parameter vector, which simply makes the training data most likely. I'm going to interpret most likely in the detailed statistical sense, but again, I think it's perfectly reasonable to say that, you know, what the learner is trying to do is to find the parameters which explain the data that they're presented with best. And then parsing involves, in fact, just simply finding the most probable structure given the terminal string or the yield, right? So this is sort of all very, very general, but I think all sort of quite straightforward. So I want to now actually give you a little bit of a feel for what a very simple statistical model over linguistic structures might be like. And I'm actually going to talk about probabilistic context-free grammars here just for a little while. So probabilistic context-free grammars are a lot like context-free grammars, except that each production is associated with a probability. It can be viewed essentially as the weight associated with it, the likelihood of using that particular production given its parent. The way in which you estimate, so in fact there's going to be a certain probability of, these probabilities are what are called emission probabilities or conditional probabilities of the rule given the parent or the left-hand side. So for example, we might associate in this little grammar down here, you'll actually see at the end of the day I'm going to associate the rule noun phrase rewrites as rice as having a probability of 2/3. Noun phrase rewrites as corn as having a probability of 1/3. Given these rule weights or rule probabilities, the way in which you compute a probability for a tree is just to take the product of all the probabilities of all of the rules that are used in that tree. So you'll see that you can do this computation, but there are 3 rules that are used in this tree here. All but one of them actually have probability 1, and the probability of the rule noun phrase rewrites as rice has probability 2/3, so the probability of the tree is probability 2/3. This sort of model has the advantage that it's very easy to also estimate these. Remember, in order to be able to solve the parsing problem, we want to be able to compute the probabilities of these trees given their strings. In order to be able to solve the learning problem, what we want to be able to do is, given a certain set of input, we want to be able to actually estimate these probabilities as efficiently as possible. I just want to point out that in the case where the tree itself is actually available, there's a very simple method which is actually optimal in a certain statistical sense for learning the rule probabilities. And that just simply is the following thing. Count the number of times that each rule is used in your training data up here. So you'll see, actually, that's what I've done. You'll see here are the rule counts. Then compute the relative frequency of the rule use versus all other rules which expand that same non-terminal. So you'll see here, for example, there are 2 rules expanding noun phrase. 2/3 of the time this rule was used and 1/3 of the time this rule was used. So in fact, we're going to make those relative frequencies the actual estimate of the probabilities of these rules. Turns out that this relative frequency estimator is optimal in a mathematical sense for this problem of estimating the probabilities of the productions on the PCFG productions. And yeah, that's really very nice. But now let me show you what happens if there are some additional constraints that we impose on the linguistic structure. So suppose that, in fact, actually our corpus was not as before, but in fact our corpus looks like the one up here. Right? So there's number agreement between the noun phrase and the verb phrase. If we just use the same estimation procedure as we used before, what we'll actually find is that we get the following rule probabilities, both for the noun phrase rules and for the verb phrase rules. When we take those probabilities, plug them back in here and compute the probabilities of these two trees, we'll find that this tree here has probability 4/9 and this tree here has probability 1/9. At this stage, we start to worry, right? And let me explain why we start to worry. First of all, we start to worry because the total sum of probabilities is only 5/9, right? Yet we're assuming that there's a number agreement constraint. So in fact, actually, these two trees are the only sorts of trees that can be built out of these words and this very simple clause structure. Where's the other probability mass gone? It's actually gone into ungrammatical sentences. It's actually sentences of the form bananas grows and rice grow, right? Sentences that our number agreement, our context-sensitive number agreement constraint rules out. Well, one thing that's actually sort of fairly standard in this literature, and lots of people have suggested this, you know, Eisler, people at Edinburgh, other sorts of things, they said, well, gee, we can fix that. And what they do is as follows. They say, let's actually call the partition function, or a normalization constant, basically simply the sum of the probability mass, which is actually assigned to all the well-formed linguistic structures. Down here, 5/9. And we'll just simply renormalize. We'll just take these numbers here and divide them by the sum of the probability mass. This is now a probability distribution, right? I mean, this is, we've in effect sort of brute forced it to these numbers here to sum to 1, 4/5 plus 1/5. But you know, things have still gone wrong, right? I mean, the probability of these, of rice grows in the input corpus that we actually estimated all these productions from was twice, the frequency was twice that of the sentence bananas grow. But our estimated grammar is now actually ranking those as 4/5 versus 1/5. It's actually saying this is 4 times as likely as this one down here. Things are actually doing even worse when you notice that if instead of using these relative frequency numbers down here, if we just simply assign, just pick out of the blue the numbers 1/2 and 1/2, redo all this computation over here again, do all the normalization again and everything else like that, you'll see actually now we get the numbers 2/3 and 1/3, which in fact actually corresponds to our input. So in fact, what this is actually showing is that once we add context-sensitive constraints, or constraints which the grammar does not directly capture, then the relative frequency estimator is no longer optimal. It's no longer estimating the production probabilities, the weights of the productions, so that the estimated distribution matches the training distribution. In fact, you can do better than the relative frequency estimator by picking things that the relative estimator, you know, values different to what the relative estimator gives you. This actually means that once we add these context-sensitive constraints, basically, these non-local constraints, the relative frequency estimator is no longer consistent. So the standard solution to this particular problem, and this is actually where all the state-of-the-art you know, statistical parsing algorithms really are at this stage, is to split the state, is to actually say, well, gee, we were wrong. There aren't just noun phrases and verb phrases. There are now singular noun phrases and plural noun phrases. And I won't bore you by going through all the math, but if you do it all, then in fact actually it all works out. If you had, you know, we get the right relative frequencies. And in effect what we've done is we've now made these non-local dependencies back into local dependencies again. But notice the price that we've paid in doing this is there's many more rules here, and there's also going to be many more of these categories. So what we're actually doing is we're splitting the state, and we pay that by seeing there's essentially an exponential explosion in the number of productions and in the number of possible states. So to summarize, what I'd like you to sort of take home from this is that if all dependencies are local or context-free, then rules are natural features of the probability distribution. Why do I say that? It's because they have a very easy estimation method, this relative frequency estimator. On the other hand, if the structures exhibit non-local dependencies, particularly if they're context-sensitive dependencies, then there doesn't seem to be any easy way to obtain natural features. In particular, the estimation problem is much harder. You're going to have to solve the problem that I'll actually lay out that mathematical problem in just a little while. And it turns out that there's actually nothing special about rule features once you move to this more general problem where you're dealing with context-sensitive dependencies. So what this actually means is that there's really no reason to restrict your attention to rule features. That is, the things that are used to define the probability distribution don't need to be just simply the frequency at which a certain production branches, but you can actually condition on, well, I'll actually suggest on anything. So at least two people in this audience I would expect probably guessed where I was going because exactly, yes. All right. So the basic form of the model that I want to suggest is exponential or log linear models. So what does this mean? The idea is that I'm going to have these little omegas here, which are my linguistic structures. I have a series of functions which map each of these to a feature value, right? And the idea that I have is that I think of a feature as being a certain configuration inside of a linguistic structure, and fj just simply counts how often the jth configuration occurs inside of the linguistic structure omega. And basically speaking, the model works as follows, right? You've got, associated with every feature, there is a parameter, lambda j, and you basically just form the dot product of the weight parameters, the lambda j, with the values of the features. This gives you, and you take the exponential of that, this gives you what I call the weight associated with this syntactic structure omega. You calculate the set of weights that are given. You calculate the sum of the weights that are given to any syntactic structure, to all syntactic structures, and then you just use that as the normalizing constant in order to get the probability distribution of a syntactic structure's omega. Why do we call this log linear? It's because if you take the logarithm of this quantity, you get a formula that looks like this, where essentially we're saying the logarithm of the probability is just a linear function of the feature values plus some constant, or minus some constant there. This might all seem extremely exotic. Why have we all of a sudden made this leap from something that seemed as natural, at least to many people, as, say, context-free grammars, to these very general log linear models? Well, I actually want to sort of point out that kind of like, is it the bourgeois gentilhomme in Candide's play, right? The chap that wanted to speak prose and then discovered that he was speaking prose all of his life. Well, those of us that have been working with probabilistic context-free grammars, in fact, have been working with log linear models for as long as we've been doing probabilistic context-free grammars. I just want to show that, if you think again of this set omega as being the set of all trees generated by a grammar, if you think of fj as just simply being the number of times that the jth rule is used in a tree, if you think of theta j as being the probability of the jth rule, then if you set this weight to be its logarithm, then you can actually imagine that, given a tree structure that looks like this, we have features for every rule. So, for example, given this tree structure here, the value of the first feature might be simply the number of times that the first rule, s goes to npvp, is used in that tree. That's 1. The value of this feature is 0 because the rule noun phrase goes to banana is not used in that tree at all. It's fairly easy to see that the probability of this tree is actually just simply the product of the rule probabilities raised to the power of the number of times that the rule is actually used. And it's also a very simple mathematical manipulation to show that that's in fact exactly equal to this log linear formula that we were using before. So in fact, the take-home message here is that these log linear models really aren't that exotic. They're a fairly natural generalization of PCFGs. So given that, what we decided to do was the following thing. We decided to say, well, let's actually take a more realistic grammar. And the largest grammar that we could lay our hands on was actually a unification grammar that people at Xerox PARC, as I said, have been building for about 15 years. This unification grammar, in fact, defines our set of well-formed structures. And I'll show you what one of these things looks like in just a moment. And we actually spent about a summer and a half devising features, which essentially are sort of things that we thought would be interesting things to condition on. You know, things that might separate good structures from bad structures. And so, as I said, each one of these features essentially counts the occurrence of a certain linguistic, syntactic configuration inside of omega. And our probability distribution is actually defined by one of these log linear models. The point I want to make at the bottom down here is this approach, as far as I can tell, is completely general. In fact, I think Professor Smolensky actually argued that this can be applied to virtually, any. It generalizes and subsumes basically any kind of grammar. This is actually what our syntactic structures look like. The details of this don't really matter, but you might be interested to see that in addition to a relatively standard syntactic tree over here, lexical functional grammar also associates every sentence with something that it calls an F or a functional structure that shows, for example, that a certain noun phrase is an object. In other words, it describes the grammatical function or grammatical role that noun phrases play. Has a lot of information about things, makes explicit information, say, for example, about tense and aspect. It says that this is an imperative sentence, for example. Null pronouns are reinserted at the functional structure, so you'll see here that let us take Tuesday the 15th. There's a null pro subject that's been added in here. Something else I want to point out is that the 15th down here is indicated that it's in a positive noun phrase, and the type of noun phrase is further subdivided into the fact that it's a date, for example. So this is a very detailed linguistic analysis in here. Let me say something about the kinds of features that we decided to use, right? So remember, what we're trying to do is that the parser is going to produce a whole host, somewhere between 10 and 100 usually, analyses of any given sentence. And we want to try to see if we can pick the right one based on the values of certain features. And we get to design those features. I think that's as much a linguistic task as designing the grammar itself is. So because we actually started on this work thinking about PCFGs, we started off by introducing rule features, as a PCFG has. But we have, you can see here, all sorts of features. One feature that we have is we count how often we see different types of grammatical relationships occurring inside of a linguistic structure. So it's fairly well known that there seems to be a general preference for preferring function-argument relationships rather than adjunct relationships, and that lets us capture that. But we also have a large number of sort of fairly specialized features. So in our corpus, there's a lot of date phrases, things like it will either be Tuesday the 15th or Wednesday or the 16th, right? And so the thing is, or the 16th is actually ambiguous as to whether or not is the 16th the date or is it something else. There's a general parallelism constraint in coordination, and in fact, you're far more likely, if one element of the conjunction is a date, it's far more likely that all the others are as well. So this parallelism and coordination constraint down here actually is going to prefer analyses, say, for example, where you see dates conjoined with dates rather than dates conjoined with something else. Okay, so I hope this has sort of given you a bit of a feel for what the model looks like. Let's actually turn to the problem of how one might actually try to learn such a model. And I want to now sort of convince you that this is...
For a given set of features?
Yes, for a given set of features. Yes.
What did you mean by the features are not independent?
Yeah, so the features are not statistically independent. So in particular, let me just pick one. One of the features that I had essentially counts the number of distinct noun phrases that you see in an analysis. Another feature counts the number of subjects that you see in an analysis. If you tell me the number of subject noun phrases there are in analysis, you've provided a lower bound on the number of noun phrases there are in the analysis. So you've certainly given me information about those. Those features certainly aren't independent. Why is that relevant? It's because a technical prerequisite for why the relative frequency estimator will work is that certain independence properties hold between the features that you're conditioning on. Those independence properties certainly don't hold in this situation, so the relative frequency estimator certainly won't be consistent. That's why I pointed that out. Okay, the point that I want to get at here is that in order to actually conduct a maximum likelihood estimation of these parameters, these weight parameters on the features, you need to be able to compute a quantity that's known as the partition function. That's the sum of the weights of all structures which are assigned, all possible linguistic structures omega. And that partition function is incredibly hard to compute. I mean, this is in fact a message from statistical physics and all kinds of things like that. And in fact, actually, one reason why that's very difficult to compute is because we actually don't know how these features interact, right? I mean, the context-sensitive interactions between constraints actually makes it very difficult to do any kind of general either analytic or numerical evaluation of this partition function. And so that actually means this maximization process here is very hard to do either analytically or numerically. Steve Abney, actually, who wrote a paper about this type of thing, wound up suggesting a Monte Carlo procedure, essentially sort of trying to draw random samples of linguistic structures up here. We started to try to do that, and it just really seems to us to be computationally intractable for realistically sized parameters. But what we actually wound up doing is actually finding a far more efficient way of doing this. And rather than maximizing likelihood, we actually maximized a distinct quantity that we call pseudo-likelihood. And what that is the conditional probability of the hidden part of the structure, the syntactic structure, given its visible part, its yield, the terminal yield string. So the way in which I imagine that is as follows, right? And summing over all possible linguistic structures involves essentially summing over all parsers of all possible sentences, and that's incredibly hard to do. But really, all we want to use this model for is sentence understanding. So all we really want to know how to do is how to pick the correct parse, these little red dots here, out of a set of competitors, right? Namely, the set of all parsers which have the same yield, have the same terminal string. So if we can learn simply how to maximize that conditional probability distribution, right, we'll actually have the information that we require in order to be able to do efficient parsing. And all this mathematics down here is really sort of just trying to write down how one formalizes that notion of maximizing this conditional probability distribution of the correct parse given the yield. So let me just sort of just go over that, right? So this quantity, this conditional probability distribution that we call pseudo-likelihood, is much easier to compute and much easier to maximize because the pseudo-partition function involves only summing over all the parsers of a string rather than summing over all possible linguistic structures. On the other hand, we wind up actually learning something that's quite different. So maximum likelihood learning essentially estimates a full joint distribution. It learns a distribution of both yields and parsers given yields. Maximizing our pseudo-likelihood learns the distribution of parsers given a yield, but actually doesn't try to learn anything about the distribution of strings. I'd actually like to suggest that that's actually cognitively more realistic as well, right? I mean, so in particular, the fact that I know English means that given a string, I can fairly accurately predict what the correct interpretation of that string is. But the fact that I know English doesn't mean that I am very good at predicting, say, for example, the question that any one of you might be likely to actually pose to me at the end of this talk. In fact, the extent to which I can predict the question that someone is going to ask actually is sort of reflects my knowledge of that person in this context, not my knowledge of English, right? And so the point here is that pseudo-likelihood essentially is giving you information about the distribution of interpretations given strings, but not telling you anything about the distribution of strings. Right?
It's unfortunate if you're doing speech recognition.
That's right. So if you want to do speech recognition, this is, in fact, actually what you want to do is pseudo-likelihood with respect to the acoustic signal, right? Not with respect to the word stream. What's that? So what is this pseudo-likelihood estimation really like? I mean, and in fact, maybe those of you that do OT theory can now actually start to see the connection a little bit emerging with OT, right?
But I have another
Yeah.
problem with this
Yeah.
notion that it's enough to get the conditional probability. You're assuming that by being able to parse a few sentences or having them as exemplars, you somehow know the conditional probability for a yield you've never seen before. And that is really something that has to do with the selection of features.
Of course.
So I wouldn't agree completely that all one really wants is the conditional probability. All one wants is a conditional probability, given the features are adequate to cover everything we haven't seen.
I guess the way I would put it is, I'd say, if I actually had the conditional probability of the parsers given the yield, let's forget about features, supposing someone just gave me that. If I actually had that conditional probability distribution, that would be as useful as having the full probability distribution over both parsers and yields for solving the parsing problem. Now, the question you're asking is, can I in fact actually come up with a good set of features? And that, to me, it seems to be sort of orthogonal to the question of whether or not I'm learning pseudo conditional distributions or whether I'm learning full distributions. You know, I mean, in fact, what you will see is the extent to which I can come up with a good set of features will reflect how good my model will ultimately turn out to be. The fact that my model is not getting everything correct shows that I obviously don't have a fully adequate set of features yet, right? I mean,
But it's more than that. So for instance, if I gave for 100,000 or whatever number of exemplars you have, if I simply gave you the conditional, in other words, I'm giving you a black box, you give it one of these sentences and a potential parse, and you spit back a number at you.
so is the question you're asking, can we learn more in principle by trying to estimate a full distribution or estimate a conditional distribution? Is that the...
What I'm saying is that learning the conditional distribution will help you parse new things only if the parameterization is such that it tells you something about sentences you haven't seen.
But that surely has to be true about also learning the full distribution as well. If I pick the features wrong and I'm trying to learn a log linear model with the wrong features, even though I might be learning the full distribution, you know, adjusting those parameters to maximize likelihood rather than pseudo likelihood, there's still no guarantee that that model is going to do well on new sentences.
That's true. So
Yeah.
I guess the problem
So that, I thought perhaps there was one thing that there is an interesting point that follows from what you're saying is in terms of efficiency of information usage, though, there is in fact a difference, right? So when we sort of go up back here a little bit, this log linear learner learns by distinguishing the correct parse from all of the incorrect parses of the same string. If there are no incorrect parses of that string, the pseudo-likelihood learner learns nothing because it's always trying to adjust the parameters so as to distinguish the correct parse from the incorrect parse. If there are no incorrect parses, there's no information to be gained. Whereas a learner that's trying to maximize likelihood can still learn something. I mean, if that sentence is if that sentence is currently extremely unlikely under your current parameter values, and you see that sentence many times and it's unambiguous, that's a very good hint that you ought to change your parameter values. Right, so. All right, so this is the, as I said, the basic framework that we're dealing with here, right? So we're given the feature values, the number of constraint violations of the correct paths, and then the corresponding information about all of the incorrect alternatives. And so what we actually have to do is to adjust these parameters, lambda here, so as to make the correct paths more likely than all of the incorrect alternatives. Right. I wanted to sort of point out a couple of things here, right? One is that there are certain kinds of features that we can ignore immediately. So in the pseudo-likelihood learner, if you ever have a feature which takes the same value on both the correct paths and all of the incorrect passes, it should be relatively clear that essentially there's no information in that feature, right? Because no matter what weight you put on that feature, it's going to help or hinder the correct paths and all of the incorrect passes to the same extent. This is actually something I'll come back to when I'm talking about OT learning. There's another kind of feature as well, one which we call pseudo-maximal or pseudo-minimal. So suppose you have a feature which always takes its maximal value on the correct paths. That's an example here. So this second feature here always takes its maximal value on the correct paths. All of the incorrect paths all have the same value or smaller. And that's true for every sentence. Well, in fact, actually, on this training data, right, this feature is actually a hard constraint, right? I mean, the hard constraint is, in OT terms, it's an undominated constraint. It says always pick the exemplar which has the most value for this feature. And we actually call such a feature pseudo-maximal. And in this framework here, the maximum when you maximize pseudo-likelihood, you actually want to set the value, the weight associated with that constraint to infinity, because there's no counterexamples to it. Similarly, also, if a feature is pseudo-minimal, you actually want to set its weight to minus infinity. And perhaps this is actually where one of the places where OT and statistical estimation part company, but certainly the statisticians that I've been working with have said that they think that that's fairly unlikely to be the right thing to do. So in particular, suppose you've got a small training corpus. Suppose the language learner certainly hasn't seen all of the language or anything even close to all of the language. Just because a feature turns out to be pseudo-maximal or pseudo-minimal over the small training corpus that you've got, that's really no reason to imagine that it's in fact pseudo-maximal over all possible data. So in fact, actually, even though the maximum likelihood estimate would be to set these lambdas to plus or minus infinity, what we decided to do is actually add a bias term. This is a kind of a prior. Yeah?
Isn't that sort of a characteristic of maximum likelihood estimation as a whole, and not just this instance of it?
That in fact, that
when you have a single mode of explanation, there's no incentive to do any other explanation besides that mode, and there's no return for seeking any other explanation except what you've got.
I don't know. I mean, certainly in many cases, you wind up seeing a probability of 1 being associated in such a situation. Yeah. In any case, what we do is we add a bias term. Essentially, we add an extra cost. So instead of just simply maximizing pseudo-likelihood, what we actually do is maximize a quantity that's written out here, which is adding in effect, it's adding a normal bias to it. So let me just sort of point out that this, I think I want to get to the optimality theory section, so I'll skip through this relatively quickly. We actually parse 2 separate corpora. We use one as a development corpus and one as a test corpus. You'll see that on average, these sentences are about 10 ways ambiguous. And we had on the order of around 200 features in both. Let me just sort of point out here that we do better, but not that much better than a relatively naive system. So a baseline estimator, which actually I should just simply say, just assigns a uniform probability distribution across parsers. So the system is just picking a parse at random and saying, I think this is the best parse. Actually, turns out to get around 88 correct in the first corpus and around 136 correct in the second corpus. And we do significantly better than that. We can get somewhere in the middle.
So what does the Charniak parse again?
Well, Charniak's parser is not producing these kinds of representations. In fact,
But who cares? It's still the sentences.
But this is the likelihood to parse.
this is actually identifying the correct parse.
Yeah, and there's going to be a probability of the
So in
parser.
so in particular, we're not just, many of these parsers have the same tree structure, but they differ in terms of, yeah, exactly. I mean, I want this, I want to get to meaning, right? I mean, I want this thing to tell me, is this a count noun phrase, or is it a date, or is it a, right? So this is considerably more refined than that. It would not.
So what kind of an ambiguity do we get? I mean, with the same,
Well,
the same structure, you actually get a lot of
so
different.
one example is, say, something like Tuesday the 15th and the 16th.
Yes.
All right. So Tuesday the 15th can be disambiguated as a date phrase. The 16th, well, maybe that's a date phrase, but maybe it's some other kind of ordinal expression. You know, maybe we're talking about Tuesday the 15th and the 16th person, right? I mean, unlikely, but it's a linguistically possible analysis. In terms of tree structures, those two analyses have exactly the same tree structure.
Around Tuesday and,
Yeah, but they have exactly the same.
16th.
Yeah, they have exactly the same tree structure. So the point is that there's a lot more to meaning than tree structures, and this is going a little bit in that direction.
You could still do the comparison, right?
I could.
You could forget
Yes.
about those features.
Yes,
and
I
just
could.
ask yourself about
I
the
could.
structure.
It also
And then the
turns.
question is,
It also.
does it do better?
It also turns out that linguistically, the Penn trees. There's an East Coast West Coast split, basically. You know, back in the days when Bresnan and Sarg and Warsaw were thrown out of heaven and went to Stanford, you know, they've actually been assigning quite different tree structures than the tree structures that Chomsky now adopts, and so it would be a significant project to actually map these tree structures into the Penn tree bank tree structures. It could be done. I actually think the big difference is going to be that, yeah, well, I'll talk about that afterwards, right? One thing that I wanted to point out here is that in terms of my overall goals, by the way, this particular parser, you know, it actually does reasonably well. Combined with the parser itself, right? Remember that I've got this detailed linguistic grammar. If I add my statistical component to it, I actually get somewhere around 75% of the sentences actually correctly parsed. That is, I actually identify the correct parse structure, which is, you know, really not too bad. One thing is that I think that it's a little disconcerting that, in fact, actually all the statistics is just done over parameter vectors, and all the linguistic structure has really just sort of disappeared. Also, the parser is just as brittle as before. Remember I said there were two big problems in non-statistical computational linguistics? This has really solved one of them, but it hasn't solved the other one. So if it turns out that a sentence receives no analysis under the detailed linguistic grammar, I'm sunk, because what I work off is the set of analyses that the detailed linguistic grammar returns.
You mentioned linguistic structure. Could some of that be captured by the feature vectors themselves? I mean, you said they weren't independent.
Yeah, so in fact, actually, that's basically, I think I'm going to skip ahead now and talk about OT, right? And in fact, that'll, what's that?
Sorry, I was just
Yeah.
Never mind. Okay, my remark was going to be that we have this problem of lack of independence too, right? And we don't mind it. I mean, you know, we're trying to make it independent in the trigram language model by doing the complementary business. but we don't need to do the.
It slows down, it messes the estimation, it doesn't change the space that the model can count.
Yes, all this. So in other words, the lack of independence just simply means that the relative frequency estimator is no longer consistent, right? So it's no longer actually maximizing the likelihood of the training data.
It also has to do with the iterative schemes for computing lambda. The more dependent they are, the slower is the convergence of those schemes.
Usually.
Quantitative
Yeah.
results, but it's not
Yeah.
empirical.
So yeah, I'd like to see if I can, I think, what time do we normally finish this? I think I was told around
Right
6.
now or in about half a minute.
In about half a minute, yeah.
No, we should give it 5 more because we started 5 minutes late.
Oh, okay, all right. I think I was actually told until 6, but I won't keep you here until then, right? So let me just simply say that one thing, how is it that I can make this model, not as brittle? One way is to trade the hard linguistic constraints for soft stochastic constraints. And it actually turns out that linguists are doing the same sort of thing in order to convert their grammars into OT, optimality theory grammars. So that's actually the reason why I started looking at these OT grammars. So I think I'll actually sort of skip the technical details of OT theory. I trust you've actually seen enough OT theory to know at least a little bit about it. Oh, right, yeah. So,
He's seeing that.
that's right. Yeah. Let me just say that for my purposes, I'm actually going to treat a linguistic structure as being an input-output pair, right? So the pair, first singular, plus also a candidate output. The idea, sort of go right ahead, I'm going to treat these OT constraints as features in my previous sense, right? And so basically, what OT writes down as being something like this, I'm now actually going to view as something that looks like this. This actually should remind you of what the input to my log linear learner actually looked like. Basically, it's some indication of what the optimal structure is, and then a set of suboptimal or incorrect competitors. And so, yeah, basically speaking, in OT terms, what you need to do is to learn a rank ordering of these here such that the optimal candidate is always lexicographically, alphabetically earlier than all of the suboptimal candidates. Whereas in my log linear learner, what I need to do is to learn a weighting of these features here such that the value which is assigned to the optimal candidate is always better than all of its suboptimal competitors.
What does the SG stand for?
Singular. This is.
Why is R singular?
No, this is the input, second singular, and the optimal output is R. So remember, linguistic
You
Second
are.
person.
yeah. So these are input-output pairs, right? So this is saying that the optimal, given an instruction to realize first-person singular, you realize that as am. An instruction to realize second-person singular, you realize that as are, and so on. And then these are all the other possibilities, right? I mean, you might imagine that you could realize first-person singular as art.
So what do the numbers mean again?
So these are actually, if I would have had a little bit more time, these are actually the number of violations of each of these constraints. So I'm thinking of constraints as what I called features before. And so basically, realizing first singular as am violates the *1 constraint once. It violates the *2 constraint 0 times, the *3 constraint 0 times, the *singular constraint once, the *plural constraint 0 times, and the faithfulness constraint 0 times, right? That makes sense? I mean, do the numbers make sense now, at least?
Still don't understand why they violate anything.
Yeah, I skipped through Joan Bresnan's analysis of this, but I think you can see, well, I mean, how many times does the feature first person appear? Right? Once, right? So if you have a *1 constraint, that constraint is violated once. These features, in this system here, these features are all going to be binary, either 0 or 1. So I just want to point out that there's a connection here. Again, in the interest of time, I'll just sort of say what it is without going through the details. If the number of constraint violations is bounded, right, that is, if you can guarantee ahead of time that there is some number C, but no linguistic object, for each linguistic object and each constraint, the number of times that linguistic object will violate that constraint is less than C. Then I make the following claim, that for any OT constraint ordering, there is some weight vector lambda such that in the OT sense, a linguistic structure is more optimal than another one. Omega is more optimal than omega prime, just in case in the log linear model sense, the probability of the more optimal structure is greater than the probability of the less optimal structure. So that's a connection. It's a fairly tight connection between log linear models and OT in the case where essentially there's a bound on the number of constraint violations. And so in fact, actually, what I've just been doing over the last week or so, just sort of essentially for fun, is to take one OT analysis that I know reasonably well, which is Bresnan's analysis of various English auxiliary systems, and treat Bresnan's constraints as features in a log linear model. And so I thought I'd just simply end with a little demonstration of some of the properties of doing log linear estimation of OT constraint rankings here. So the first thing I want to point out is that, in fact, first of all, this learner that I've got, which actually is changing these parameter weights, learns very quickly. Starts off getting no examples correct, and within 2 iterations, it's actually, I just give it the full English paradigm. I am, you are, he is, we are, you are, they are. Within 2 iterations, it's basically learnt all those examples. This quantity here is actually the conditional probability of the correct analysis given the yield, right? In other words, it's comparing the correct analysis to all of the incorrect competitors. And you'll see the log probability very quickly approaches 0, which means that the probability is very quickly approaching 1. It's actually kind of interesting to look at what happens to these values, right? And in fact, let me just simply say that if you just simply try to maximize pseudo likelihood, very quickly the parameter values for, well, I guess the first thing to note is this is, when Bresnan devised her grammar, not only did she identify the features or the constraints, but she also came up with a constraint ranking, so it would generate English and a whole lot of other dialects. The constraint ranking that Bresnan chose for standard English was this one. And in fact, the pseudo-likelihood learner identifies this particular ranking here. In other words, it's a ranking which is consistent with Bresnan's ranking. When you actually look at the parameter estimates that the pseudo-likelihood learner comes out with, you actually notice that these parameters here are actually going very, very quickly up to, let me just tell you, they're going to infinity. The reason why the computation stopped here is because e to the 200 or e to the 300 is a very large or a very small number, as the case may be, right? In fact, actually, these features here are what I call pseudo-maximal features, right? I mean, these things that are undominated constraints are things which in the log linear framework are things for which you'd actually like to give a parameter value of infinity, right? Because any candidate which has these constraints or these features is a loser, basically. So, in fact, actually, in all the examples I'll show from here on in, I actually add this parameter bias that I was telling you about before, right? This is, and all that does is it simply says is, you can view that as saying, don't make these numerical quantities any higher than you need to in order to correctly classify your input. That's a very crude way of describing what this bias is all about. So you can see here I've done exactly the same experiment. I get exactly the same orderings of constraints, but now these quantities are actually very nice. They stay nicely bounded. One thing that I think is sort of kind of interesting is that we actually seem to be sort of discovering sub-symbolic structure, to use a phrase that someone in this room I think has used before, right? So in other words, we're actually seeing interesting sort of refinements of the ordering. This example here is just showing that I've actually tested this on not just standard English, but on all the English dialects that Bresnan describes, and in fact it comes out with constraint rankings which are consistent with what Bresnan says. There's an interesting case here that Bresnan actually gives, the one case I could find where the constraint ranking that the pseudo-likelihood system comes up with is different to the constraint ranking that Bresnan gives in her paper is this one, which is where you can see here the star plural constraint is much higher valued than the star 1, star 2, and faithfulness constraints. These are all three essentially have the same value, and they're above singular and third person. So the one thing that's interesting here is that in fact, unless I'm extremely mistaken, there's another constraint ordering for which you would actually generate the Southern and East Midlands dialect of English. Namely, that's one where you actually put faithfulness and star first and star second as being equally ranked. You'd still generate the right output. So in fact, the pseudo-likelihood learner has found a different but equally good analysis of this data. Okay, one thing I'd like to point out is that unlike, say, standard OT learners, frequency matters in the pseudo-likelihood learner. So as we change the relative frequency, the number of occurrences of the sentence in the training data of I am, so I just have one occurrence of everything else, but I have between 0 and 10 occurrences of I am, the I am sentence in the training data. In fact, actually, what I find is that it's interesting, the constraint rankings overall don't change, but the actual constraint weights do change. I guess actually I see a slight change between first and third person down here. So unlike OT learners like the Tessar and Smolensky learner, this learner here actually exhibits frequency sensitivity. And I think that actually, I would be extremely surprised if children don't exhibit frequency sensitivity in their learning as well. And then finally, just as another little point of comparison, the Tessar and Smolensky constraint ranking learner essentially sort of throws up its hands when it's faced with inconsistent input. But it seems to me as if that's not terribly cognitively realistic either, right? I mean that in fact a learner really ought to be able to actually deal with the fact that sometimes they've either misheard or else they've actually, what about the poor child that's actually living on the border between Standard English and Somerset English, right? And it hears both kinds of examples, right? I mean, learning doesn't just completely fail there, although maybe that's actually I don't know. But anyway, this learner here, you'll see if I actually change, in the input data here, I have one example of thou art, and I actually change the number of occurrences of you are. And you'll see actually, we start off only getting 5 out of the 6. This is the number of standard English examples that the learnt constraint ranking gets right. So, of course, at this stage, it's learning thou art instead of you are. And in fact, at this stage here, it's also thoroughly confused. It's not preferring you are over thou art. But very quickly afterwards, once there's more occurrences of you are, it's actually learning you are and not thou art. It's interesting, however, that it never actually learns the OT correct constraint ranking. So I've actually, looked at this much further out than just simply 1 to 10. It seems as if even though these numerical weights are actually sufficient to prefer the correct form you are over thou art, the one occurrence of thou art actually is sort of still sufficient to change this ranking so that star 2 is below faithfulness. Well, Anyway, so what are the conclusions of this little section here, right? I mean, I think that, in general, what I've been trying to argue is that log linear models provide a systematic framework for defining probability distributions over linguistic structures. Pseudo-likelihood estimation provides a practical way of estimating these conditional log linear models. And then I've also talked a little bit about the relationship between OT and log linear models, pointing out that OT constraints can be used as features in a log linear model, and that the constraint rankings that you get from the log linear learner, the pseudo-likelihood learner, are often very, very similar to the constraint rankings that linguists give by hand when they're ordering OT constraints. And I'd also like to suggest that pseudo-likelihood estimation may actually be interesting for people that are working in an OT framework, because it seems to be more robust to noisy data than current OT learning frameworks. Thanks very much.
So, first of all, how do we know that that a particular analysis is correct? I mean, do they have a tree bank that's done ahead of time, or do they just say how true?
Yes, I'm afraid I skipped over that section. So the people at Park have not only written the big grammar, they've also parsed, as I said, several of their corpora. They've worked both on the verbmobile corpus, that's a corpus, right, and then also this corpus of sentences that they extract. And then they've then also hand-corrected those parsers.
Right, and it's ahead of time.
That's right. And so I did a tenfold cross-validation experimentation.
And so now how do you, so for instance, if something has 186 parts,
right,
that means that the grammar produces all 186.
That's right.
And you just let this thing run on
That's
every one of them.
So actually, so do you
don't have a good search process.
No, so actually, shall I tell you a little bit more about, I mean, I didn't talk about this detail. The non-statistical parser that is used produces what are called packed feature structure and parse tree representations. So these are things which, packing can be done for trees so that you can represent an exponential number of trees in polynomial space. The packer that they've got for tree feature structure combinations is not guaranteed to be polynomial, but tends to be polynomial in most cases. So we've actually been working with an evaluator and unpacker combination in parallel, right? So we essentially enumerate the analyses, evaluate the analysis, and then throw it away.
Well, you evaluate
that's
all
right.
of them,
We
and
do,
you,
yeah.
And you take the
That's
best
right.
one
Yeah.
and then compare it with something that's stored
so this
ahead of
is,
time.
yes, so this is, let's see if I can justify why we do that. I mean, this is really just a proof in principle that something like this can be done, right? And also notice that, 100 or 200 analyses is really not too not too bad. I mean, I think in the speech recognition literature, you often work with n-best lists, which contain on the order of 100 or 200, right? So this is in fact, in a sense, sort of very, very much like that, yeah.
And these grammars are good enough so that when honestly running on the test corpus, at least one analysis is identical to the...
no, in fact, I believe what is... No, so they're not robust, right? I said that the systems aren't robust, and that's because these grammars aren't robust. The reason why these grammars parse the test corpus is because some linguist has sat down and essentially, run the parser over each sentence on the test corpus.
So it's standard linguistic cheating.
Well, or you might say, or else you might just simply say it's a step on an incremental development cycle, right? I mean, yeah. No, look, I agree with you. Yeah. And in fact, as I said, I think some very interesting things to try and do would be to try and take one of these OT-based learners, because that trades hard constraints for soft constraints. I think that a big part of the problem here is that in order to try and reduce the ambiguity, these guys have added more and more linguistic constraints. And what that does is it actually rules out the correct analysis in many circumstances. Yeah. I think it's actually very difficult to tell, actually, at this stage, whether you know, the problem is just simply that we don't have the right constraints. That is, that there is some correct constraint on, say, the distribution of, you know, empty nodes. And we have come up with another constraint which is close but not quite right. Right? And in that case, right, that constraint may actually help us resolve certain ambiguities, but it may also lead to non-robustness. Right? Is that the situation? Or is it the situation that basically something far more general needs to be done? I mean, I also think that there's something, we can understand completely, you know, or not completely, but very ill-formed input. And I think that what that suggests is that our interpretation process is not taking the output of parsers produced by a grammar that only produces completely grammatical structures. You know, we need to have some mechanism for interpreting, you know, ill-formed input. Yeah.
Thanks for a great talk, especially results on learning. My question is about incremental processing. As you hear a sentence incrementally and more feature values are revealed, the weights lambda that you use, in some sense that tells you how useful that information about those features was, right? I was wondering if you might speculate a little bit on the cognitive significance of those values lambda.
Oh, gee, that's a very hard thing. Let me just simply say one thing that makes it actually very hard to even think about incremental processing here is that in the PCFG world, the probabilities associated with a rule are always less than 1, right? In this world here, the lambdas, which are essentially the log probabilities, right? They need not be less than 0. In other words, they can be positive, which corresponds to actually having it would be the same as in a PCFG of having a rule weight which was greater than 1, essentially saying I prefer bigger structures rather than smaller ones. What that means for incremental processing is that in the PCFG world, you have a nice monotonicity property. If you have a partial parse tree, you can be guaranteed that as you extend that parse tree, the probability of that tree and all of its descendants will only get smaller. In this world, if you've got a partial analysis and you start to extend it, it's actually possible for the probability to actually grow. That is, its more elaborated versions actually have a higher score than the structure that it came from. And so I think that lack of monotonicity may actually pose a problem.
Let me just add a follow-up thing. Do you think that could cause local minima for an incremental maximizer with an incremental processor?
Oh, sure. Yeah. I mean, we know that happens in PCFG parsing as well. That it's I mean, when you probably know about Brian Rourke's work, yeah, right? I mean, that's the reason why people need to do beam search rather than just simply best first search. So this is highly unlikely to be better and almost certain to be worse than that. Yeah.
Go ahead. I want to come back to this conditional model versus the joint model.
Right.
Now, you can work out that the conditional model, if I had a set of lambda features and the lambda, then I decided to estimate conditional models. It's the same as not having a conditional model, but instead throwing in one more feature of any configuration, which is essentially a feature only of the yield, and which says, did I see this in my training? Yes, no. And the way it works out is that it's one of those hard constraints which flies off to infinity, and you're back to re-estimating the usual model.
Are you talking about, I mean, where I learned a lot of what I know about log linear models was in Professor Jelinek's book. So you're talking about what's called in there the optimization, the adding an extra feature H?
No, I'm talking more about a conditional model is essentially the same as a regular model without conditioning, except that you're putting in an additional constraint on the frequency of things, of the things you observe. So I'm not quite sure what Fred talks about in his book, but if it was language modeling, it's like saying that the frequencies of the histories will be exactly those that I see in my training models.
Yeah, that's what
Yeah,
must be.
and so that's really what it's, and that if you add those as additional constraint, then you don't need to think of this as a conditional probability estimation anymore. You can think of it as a full model and go ahead and do it. What happens is that by putting this as a feature, you actually simplify the computations, and that's why the partition coefficient.
I think it is in fact actually the case that what I did and what Fred described in his book are in fact the same. We came to it by thinking about it in terms of these conditional probability distributions, but I remember actually going through that section and thinking that yes, that's the
right, and
that's
actually that's the feature that makes me a little less comfortable with conditional models than I would have otherwise been, because most of the other features I can find justifications for having them. But because conditional models amount to having this feature, have I or have I not seen this sentence before? I worry that conditional models.
Actually, it's how many times have I seen it?
How many times have I seen it? It makes the conditional models a little. In terms of, like, whether the rest of the features make any difference to the two ways of doing things.
You'll actually have to explain that to me, because I don't see how that feature is the number of times that
So what happens is, if you come across a history you have never seen, first of all, on any parsing problem, this feature is going to appear both in the numerator and the denominator, and it's just going to fall out. So it doesn't affect your model at all. It cancels out. But the thing is that it amounts to making this assumption, which I somehow feel that it puts more burden on your other features to make up for this bad feature. In other words, regardless of what it does mathematically, somehow.
I'd be very interested to see. I'm not so sure I follow that, but I'd be very interested to see it. I do know, as I said, that in a sense, this is a less efficient learner. I mean, this learner is only learning. One aspect where this is actually very cognitively unrealistic, I think, is that this learner is actually learning only in situations where a sentence has a correct parse and some incorrect parses. In other words, when it has unambiguous input, this learner learns nothing. And I think that's actually fairly unrealistic. Now, actually, one thing that's interesting is you can also turn this around. In fact, the way in which I talked about this log linear learner in the OT case was where I didn't have time to go through this, but I actually think of you're thinking of the conditional likelihood of the linguistic structure given the meaning rather than given the string. I actually call that semantic pseudo-likelihood. And that, I think, is actually far more cognitively realistic, right? I mean, when does a child learn something from its input? It's precisely when a given meaning might be expressed in several different ways, and the child hears that that meaning was in fact expressed in one particular way, right? In other words, the child learns something from the fact that, I chose to express a transitive verb frame in English in a noun phrase verb noun phrase structure rather than in, say, a Japanese noun phrase verb structure, right? So even though those inputs may not be ambiguous going from the string side, right? There's two noun phrases and one verb, so it's very likely to be a transitive verb structure. The fact that a transitive verb structure might universally be realized in any one of those two or possibly more ways is actually something that a learner can exploit in order to learn something about the property of the language that they're seeing. So, yeah, if you're interested, I can actually show you how you turn all this around and actually use semantics rather than the string in order to drive the learning process.
Last question. You have a question, right?
Well, so what are the prospects that the information that your parser uses to generate the candidates, that information can be recoded as constraints of the same sort that you're using to estimate likelihoods?
So you're saying, to what extent do you think we can actually integrate the?
I mean,
I think no, exactly.
You should do.
Yeah, exactly. I mean, so here's one project that this is my summer project actually, is to try and see if I can take a very general language model, say a PCFG that's extracted from a tree bank. So I'd now be generating a lot of different trees for any given string. And then actually what I'd like to do is to go through the OT literature and take a look at various different constraints that you and Geraldine and other people have proposed. As essentially things that would perhaps give me, and I'll use those as features to try to see if I can identify which of those trees are more likely to be correct and which ones aren't. I haven't talked about learning from unlabeled data here, but it turns out that there's a project that I and Stefan Riesler in Germany are involved in, where we're trying to extend EM, expectation maximization, to try to see if we can actually learn from unlabeled data. So that would be a move in that direction that you're talking about. Essentially, we would then have a framework essentially where there's a very weak component which is proposing candidate structures, and we'd probably be generating on the order of hundreds of thousands of candidate structures per sentence, and then we're then going to try to see if we can then prefer the, identify the correct one. Yeah. I'll let you know how that works.